Welcome everybody to our business math course. Today we are discussing curve sketching. In order to sketch a curve, we need to know how to find the intervals on which a function is increasing or decreasing. We need to find the critical values of the function. We need also to find the relative extrema of the function. Also, we need to test for concavity and inflection points if at all they exist. Finally, we end our section discussing asymptotes and giving some examples to sketch the graph of a function. This is Magda Talib Al-Hinai from Sultan Qaboos University, and I welcome you all. We start our presentation discussing decreasing and increasing functions, and let's start with a curve. Here is the x-axis, the y-axis, and the curve of f of x. We will see that this is a decreasing function simply because if I take a point x1 here and another point x2 here, we find that f of x1 is larger than f of x2. So let's see this on the graph. Here is x1 and x2. Here is f of x1, here is f of x2. We see that this function is decreasing because x1 is less than x2, but f of x1 is larger than f of x2, and in such case we say the function is decreasing. So we write this, a function f is said to be decreasing on an interval a, b, if x1 is less than x2, then f of x1 is greater than f of x2. Now, let's draw a tangent line here, and another tangent line here, and another tangent line here. Whenever we draw any tangent line to this curve, we see that this is slanting to the left, meaning that its slope is negative. So in other words, we say that the function is decreasing if f prime of x is less than 0 for all x in the interval a, b. Now we move to increasing functions, and again here is the x-axis, here is the y-axis, and here is the function f of x. We see that this is an increasing function. Yes, if I take 2 points x1 and x2, and I find f of x1 and f of x2, we see that f of x1 is smaller than f of x2, and hence we say that the function is increasing on the interval a, b. So we see whenever x1 is less than x2, then if we have f of x1 is less than f of x2, we say that the function is increasing. Okay, we apply the tangent idea also. We take a tangent line here and another tangent line here and another tangent line here. We see that all of these tangent lines are having positive slope. So this is another criteria for saying that the function is increasing on the interval AB. We write it as follows. If f prime of x is greater than 0, the first derivative of the function is positive at any x in AB, then f is increasing on AB. Now we move on to the coming slide and see how can we find the critical value. In the present slide, we are going to talk about critical values. For a function f of x, the value x equals c is called critical, but we have to make sure that this c is in the domain of f. Okay, we call it critical if one of two conditions happens. The first one, if c makes the first derivative equal to 0, or if c makes the first derivative undefined, not existing. Okay, now we move further to talk about the tests for relative extrema. These are also very important for us whenever we are trying to sketch any curve. We have the first derivative test. For a continuous function f on an interval ab that contains the critical value c, where f is differentiable on ab, except possibly at c, we have f prime of x changing its sign from positive to negative as x increases through c, then in such case we will say that at c f is having a relative maximum. Also, if we have f prime changing its sign from negative to positive as x increases through c, then we say that f has a relative minimum at c. We have also the second derivative test. The second derivative test is not always successful. We say, suppose that we have the first derivative equal to 0 at a point at a value for x c. If f double prime of c is less than 0, then we say that the function attains its maximum at x equals c. Also, the second case, if we have the second derivative of f evaluated at c greater than 0, then we say that f has a relative minimum at x equals to c. The third situation, when the test fails, when f double prime of c is equal to 0, in such case we say that the second derivative test fails and we have to go back to the first derivative test. To continue our session, where we need to know how to sketch a graph, we need to talk about concavity, and we will do this in the coming slide. In the present slide, we are going to discuss the concavity of a function. We start by concave up functions. Suppose we have this curve representing a function f of x. We say that this curve, we can see it's concave up. Okay, let's try to join any 2 points on this curve. Whenever we think of joining these 2 points, we find that the line joining them is lying above the curve. And here we go, and here we go. Any line joining any 2 points on the curve, we find that the line is lying above the curve. We call the curve concave up. Okay, suppose we have a function f that is differentiable on an interval ab. We say that this function is concave up if its first derivative is increasing on a b, if f prime is increasing on a b. And the word increasing tells us that the derivative has to be positive on a b. What's the derivative of f prime? It's f double prime, yes. So the criteria will be if f double prime of x is greater than 0 for all x in AB, then we call f concave up on AB. In a similar way, we talk about concave down. We will draw the curve and we will join any 2 points on the curve. We will find that the line joining any 2 points on this curve is lying below the curve. In such case, we call the function to be concave down. Again, for a differentiable function on AB, on an open interval AB, we call the function concave up if the first derivative is decreasing on AB. And we mean by decreasing that the derivative has to be less than 0. What's the derivative of f prime? It is f double prime. So the criteria will be f double prime of x is less than 0 for all x in the interval AB. Then in such case, f is concave down on AB. Now we move to the inflection point. A function f has an inflection point at a if and only if it is continuous at a and changes its concavity at a. Let's take an example. Test the function f of x equals 6x power 4 minus 8x cubed plus 1 for concavity and inflection points. Here we have to find the first derivative of f of x. The first derivative of f of x is 20. We have 6x power 4 will be differentiated to 24x cubed. We have minus 8x cubed will be differentiated to minus 24x squared. We have the 1, it will be differentiated into 0. Now we get the derivative of the first derivative, so we need to find f double prime. F double prime of x is equal to, what's the derivative of the first term in f prime? 24x cubed is differentiated to be 72x squared. and we differentiate minus 24x squared to be minus 48x. Now we put the second derivative equal to 0 and we try to find the values at which the second derivative is 0. We need to find what are the values for x so that the second derivative equals 0. We can factor the 24x as a common factor. So here we have 24x multiplied by 3x minus 2 equals 0. And this will make it easier for us to see that x equals 0 makes the second derivative 0. Also, x equals 2 over 3 makes the second derivative 0. Now we take this 0 and the 2 over 3, sorry, to the real line. We put them on the real line, yes, and we start investigating the sign of the second derivative in each interval, from minus infinity to 0, from 0 to 2 over 3, from 2 over 3 to infinity. Let's consider this interval. We put our second derivative as 24 multiplied by x multiplied by the bracket, and we take any test point in this interval and we study the sign. We investigate the sign of this product. So we take, for instance, minus 1, it can work, minus 2, minus 10, minus 100, anything. We care only for the sign. Minus in this part will give us a minus for the x and a minus for what's inside the parentheses. Minus times minus is positive, so it tells us that in this interval the second derivative is greater than or equal to 0 because it's positive in this interval for all x in this interval. So we know that this is concave up. We do the same thing here between 0 and 2 over 3. We put the second derivative and we study the signs. We take a test point between 0 and 1 over 3. The easiest for us is to take between 0 and 2 over 3, sorry. The easiest for us is to take the 1 over 3. So we put 1 over 3 here, we get a positive. We put 1 over 3 here, we get a negative. Let's see. Yes, this is positive, this is negative, and then the product is negative. So we have that f double prime is less than 0 in this interval, telling us that the function is concave down. Now we move to the third interval and we put our second derivative and we take any test point in this interval. Anything greater than 2 over 3, it can be 1, it can be 10, it can be 100. Whatever we plug in here, we get a positive here and a positive here. So we have 24 times positive, so the whole thing is positive. So we understand that the second derivative is positive for any x in this interval, tells us that here the function is concave up. Now, we notice that the function changes concavity to the left and to the right of 0. So we can call, according to the definition, we call 0 a value of x where we have an inflection point. And whenever we say the word point, we mean that we want to have x coordinate and y coordinate. So the x coordinate is 0, the y coordinate, we put 0 here and we put 0 here, we put 0 here, we get y is 1. Also, to the left and to the right of 2 over 3, we find that the function is changing concavity, and 2 over 3 is in the domain of the function f, and the function is continuous at 2 over 3. So here we also call 2 over 3 to be, the function will have at 2 over 3, it will have a point of inflection. The x-coordinate of this point of inflection is the 2 over 3 itself. The y-coordinate, you take this 2 over 3, you go to the function f of x, plug in the 2 over 3, and calculate the y corresponding to the 2 over 3. You get the point of inflection. We move on. Slide and the coming slide, we are going to sketch the graph of the function y equals 2x cubed minus 9x squared plus 12x. As a first step, we find the x and the y intercepts, and in order to find the x-intercept, we put y equals 0, we factor and find the zeros of y,
We have here x times the bracket. This bracket, according to the discriminant, is not zero for any real number x. So the zero comes from this part. So at y equals 0, x equals 0, and this will be the x-intercept. In a similar way, we find the y-intercept putting x equals 0 in the above equation, and we get also y equals to 0. In the coming step, we find the critical values of the given polynomial. So we differentiate, we find the first derivative to be 6x squared minus 18x plus 12. And then we take this first derivative, put it equal to 0. After factorization, we get either x equals 1 or x equals to 2. These are the critical values. Then we study the intervals on which the function is increasing or decreasing. We take the 1 and 2 to the real line, and we split the real line to 3 intervals. The first interval will be from minus infinity to 1, and on this interval we study the sign of the first derivative. We take any test value, let's say 0, we put 0 in the first bracket, 0 in the second bracket. We get minus times minus is positive, telling us that the first derivative is positive on this interval, so the function is increasing from minus infinity to 1. And on the interval from 1 to 2, we do the same thing. We put the first derivative, we take a test point, let's say 1.5. We plug it in the first bracket, we get a positive. We plug it in the second bracket, we get a negative. Positive times negative is negative, so the first derivative is negative between 1 and 2. Then we move to the third interval from 2 to infinity, and we put the first derivative, taking any test point in the third interval from 2 to infinity. Let's say we take x equals 3, 3 minus 1, 3 minus 2, positive times positive, we get positive. So the first derivative is positive on this interval, telling us that the function is increasing on the interval from 2 to infinity. Now we move on to find the relative extreme. We see here that the function is increasing to the left of 1 and then decreasing to the right of 1. So at 1 we will have a relative maximum. So y of 1 is equal to 5 from the first equation. We put 1 here, we put 1 here, we put 1 here. We get y of 1 is a relative maximum. So the maximum point is at 1 and 5. We do the same thing at x equals 2. We see to the left of 2, the function is decreasing. To the right of 2, the function is increasing. And then we say that at 2, we have a relative minimum, which is calculated from the given equation, where we remove every x and we put 2 to get y of 2 equals to 4. So the point 2 and 4 is representing the relative minimum of the function y. Next, we move to study the concavity, test for concavity and inflection points. In order to study concavity, we differentiate y prime to get y double prime equals to 12x minus 18. Put the second derivative equal to 0. Get the corresponding x. We have x equals to 3 over 2. Take this 3 over 2 on the real line and study the concavity, meaning study the sign of the second derivative to the left and to the right of 1.5, which is 3 over 2. On the interval from minus infinity to 1.5, we take any value for x, we put it in the bracket, 2 times 0, for instance, minus 3, we get a minus, telling us that the second derivative is negative on this interval, so the function is concave downwards. While on the right of 3 over 2, we have the second derivative. Its sign is positive, so it tells us that the function is concave up on this interval from 3 over 2 to infinity. What about 3 over 2 itself? The concavity changes to the left and to the right of 3 over 2, and 3 over 2 is in the domain of the given function, which is a polynomial, which is defined for all real numbers. So the 1.5 is a point of, we have a point of inflection at x equals 1.5. We calculate the corresponding y coordinate. It will be 4.5. We get it from the first equation, this one, where we put x is 1.5 to find y to be 4.5. Next, we move to the coming slide where we will do the sketching of the curve in the framework of what we found on. Now We start sketching the graph of the function in the framework of the results we found in the previous slide. Here we put the x and the y axes, and we start with the x and y intercepts to put them on the graph. We know that the x and y intercepts were 0 and 0, so here comes the 0 to sit in its place, the 0 and 0 to sit in its place, the origin. Next, which way should the curve go? This way or that way? In order to decide, we need to know the end behavior of the function, so the curve representing the function. So here we put the function in front of us. We see that the leading term is 2x cubed. So we are talking about x cubed. This is the curve of x cubed when we have the leading coefficient positive. So as x goes to infinity, y goes to infinity, and we represent this on our graph by this n terminal. We put this going to infinity as x goes to infinity, and also as x goes to minus infinity, y goes to minus infinity. Here comes the n terminal of our curve. Next, we move to the relative maximum that y has at the point 1 and 5. So we put the 1 and 5 on our xy plane, and we put this U shape to say that this is representing a maximum. Now, here's the 1 and the 5. In a similar way, we put the 2 and 4 on our graph. Here comes the 2 and 4. It is representing a minimum, so we will have this U shape representing the minimum. Also, we will have the point of inflection, which is 1.5 and 4.5. We will have it on our graph in front of us. Now we start thinking of the function on what intervals is it increasing and or decreasing. So the y is increasing on the interval from minus infinity to 1, also from 2 to infinity. So here it comes, it's increasing to the left of 1. It will continue to increase until it reaches the maximum at 1, which is 5. Then to the right of 1, in the interval from 1 to 2, the function will be decreasing as we see in front of us, and then it will continue to increase from 2 to infinity. Now let's see also on the curve. Can you see to the left of 1.5, it is concave down, and to the right of 1.5, the function is concave up as we expected. Yes, so this was a good illustration with an example, a cubic polynomial, how to sketch it, and we move on to see the asymptotes.
In the present slide, we are going to introduce asymptotes. An asymptote is a line touching the curve at a point at infinity. We have the vertical asymptotes and the horizontal asymptotes. Also, we have the slant asymptotes, which we will postpone to a future discussion. A vertical asymptote, the line x equals a, we call it a vertical asymptote of a function f if and only if it satisfies either limit f of x as x approaches a from the right is equal to plus or minus infinity, or limit f of x as x approaches a from the left is equal to plus or minus infinity. If we have a rational function where we write f as a polynomial over polynomial, and the line x equals a is called a vertical asymptote if and only if it is a is a zero of the denominator and p of a is not zero. Let's take an example. We have f of x equals x over x squared minus 4, and we are asked to find the vertical asymptotes. We factor the denominator. This is the difference between two squares, so we get the zeros of the denominator is either plus or minus 2. So x equals minus 2 and x equals plus 2 are the vertical asymptotes. Now let's move on to see the horizontal asymptotes. Okay, we define the line y equals b to be a horizontal asymptote of the function f if and only if it satisfies one of the following conditions. If we take the limit of f of x as x goes to infinity, this limit is equal to b. Also, another condition, if the limit of f of x as x goes to minus infinity is equal to b, then y equals b is a horizontal asymptote. Let's take an example. Given f of x equals 2x squared over x squared plus 3x plus 4, we are asked to find the horizontal asymptote. So we take the limit of f of x as x goes to infinity. We know that this is a polynomial. The degree of the numerator is equal to the degree of the denominator. So the answer of the limit is equal to 2, and y equals 2 is the horizontal asymptote we are looking for. Now on this slide, we take an example to see how can we sketch the curve of the function f of x is equal to 1 over 4 minus x squared. We'll give you the first derivative and the second derivative, and we start calculating the intercepts. For this function, we see that if we try to find the x-intercept, putting y equals 0, this is never 0, so we don't have x-intercepts. But for the y-intercept, we put x equals 0, we get y is equal to 1 over 4, and this 0 and 1 over 4 is the point which is giving us the y-intercept. Next, we find the critical values of the function. We take the first derivative, put it equal to 0. We find that the first derivative is 0 when x is 0, and it is defined when x is equal to plus or minus 2. 0 is in the domain of the given function, but unfortunately, plus or minus 2, they are not in the domain of f, so they are not critical values. Next, we find the intervals on which the function is increasing or decreasing. We take the 0, the plus or minus 2 to the real line, and we start studying the sign of the first derivative. Here we have the denominator on all intervals will be positive because we have the denominator is a bracket squared. The sign will differ according to the numerator. In the interval from minus infinity to minus 2, we take any test point, we get minus over positive. So the first derivative is negative less than 0 on the interval from minus infinity to minus 2, telling us that the function is decreasing on this interval. From minus 2 to 0, we move on and we try to test the sign for the first derivative. We have again the denominator is positive as I said, and any test point in the interval from minus 2 to 0 will give us a minus. So the whole thing will be minus. The first derivative is less than 0 on this interval, telling us that the function is still decreasing between minus 2 to 0. We move to the interval from 0 to 2. We take any test point and we test the sign for the first derivative. We have plus over plus. So the first derivative is positive, telling us that the function is increasing on the interval from 0 to 2. We take any test value in the interval from 2 to infinity. We have positive over positive. So the first derivative is positive greater than 0, telling us that the function is increasing from 2 to infinity. Okay, we move on and we try to find the relative extrema. We see one here, the function was decreasing until it reached a minimum and then it started to increase. So at x equals 0, we have a relative minimum for the function and we calculate the minimum value. Taking 0 up here, we get 1 over 4. So we move on now to test for concavity and points of inflection if they exist. We have the second derivative can never be 0 because we have again x squared times 3 plus something positive. This is never 0 for any real x. So we do not have any x which will make the second derivative 0, but we have the second derivative undefined for plus or minus 2. But remember, they do not belong to the domain of f. So, but we'll still study the concavity or the sign of the second derivative to the right and left of each of these values. To the left of minus 2, from minus infinity to minus 2, we take any test point. We have a positive numerator. We take any value, we will get a negative denominator, so the whole thing will be negative. The second derivative is negative on the interval from minus infinity to minus 2, telling us that the function is concave bound on this interval from minus infinity to minus 2. Now we move to the interval from minus 2 to 2 and we take any test value. We test for the sign of the second derivative. We find it to be positive, meaning that the second derivative is greater than 0 on this interval between -2 to 2. So the function is concave up on this interval. On the interval 2 to infinity, we test the sign. We get a minus sign for the second derivative, telling us that the function is concave downwards on this interval. And here we go. Okay, so we find that the concavity is changing to the left and to the right of each of -2 and 2, but we cannot find a point of inflection at any of these because the word point means that we need to have an x coordinate and a y coordinate, and we cannot find the corresponding y because the function is undefined at ±2. And we move on to the coming slide where we will find the vertical and horizontal asymptotes, and then we start sketching. We continue our work to find the vertical and the horizontal asymptotes of the given function. We have the zeros of the denominator will give us the vertical asymptotes, and these are x equals to -2 or x equals to 2. So we have two vertical asymptotes, x equals -2 and x equals 2. We move to the horizontal asymptote. We take the limit as x goes to infinity. We find that this limit is equal to 0 because the degree of the denominator is less than that of the numerator. So we have y equals 0 as a horizontal asymptote. These are the three asymptotes we have. Now we try to sketch, and in order to sketch, we will take the results we got in all the problem from the last slide and the current slide. We have no x-intercept. The y-intercept is 0 and 1 over 4. So we draw the xy axes, and here we go with the y-intercept. At the y-intercept at 0 and 1 over 4, we have a relative minimum. So there we go, and we put the cup representing that there will be a minimum here. Moreover, we go and take the vertical and horizontal asymptotes, which we've just got here, and put them on the xy plane, as we see. So now we need to know the end behavior of this function. The ends, will it be touching the curve at infinity from this side or from this side? Going to minus infinity from this side or from this side? Here also, from which side? And the same thing here, from which side? In order to do that, we have to study the end behavior, and we do the following table. So we take x goes to -2 from the left and -2 from the right, and we see where will f go. If we try to take something very close to -2 from the left and we plug it in here, say -2.1, we will get something negative, and it keeps getting, the denominator keeps getting smaller and smaller as we get closer and closer to -2. So the whole fraction will get bigger and bigger, so we put minus infinity. In the same way, we do the same thing when we think of -2 from the right. When we get to -2, closer to -2 from the right, say we take -1.9, we get closer and closer to -2. This gets closer and closer to 0, but the sign is positive, so we will go to plus, we'll put plus infinity here. The same thing we do when we get closer to positive 2 from the left and we get closer to positive 2 from the right, and we try to find the signs, we will find them as follows in front of you in this table, and we are able now to put the ends as we see to the choices given to us by this table. Next, also we have the horizontal asymptotes. We see that this end should be here, not above, because the curve will not intersect the x-axis. As we know, there are no x-intercepts, so we have to put this end here, and the other end, as x goes to infinity, we put it here, not on top of the curve. Otherwise, when we connect, it will cut the x-axis. Now we see that the function y is decreasing on the interval from minus infinity to -2, also from -2 to 0. So we put this on the curve, yes, and we see that it is increasing from 0 to 2 and from 2 to infinity, we put this on the curve. Yes, we get this. And now let's see what happened to the concavity. It's in agreement with what we've got. It is concave down on the intervals from minus infinity to minus 2, and from 2 to infinity, this is concave down. And here between minus 2 and 2, it is concave